Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video. All math-based, of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on inside as we jump into section 5.6 of the Big Ideas Math Integrated Math 3 textbook. This is on modeling with exponential and logarithmic functions. This is the last section of chapter 5 as well. So we're putting it all together. Well, I shouldn't state that. Not necessarily putting it all together, that's what the review's for, but taking anything that you learned so far into now is considered fair game. We've seen the modeling things before with linear functions, absolute value functions, quadratic functions, and even cubics and quartics and things like that. And I think some other ones like that will pop up so we know to differentiate exponential versus quadratic, things like that. So I think those are kind of fair game to be a part of your questions here. So I guess we're bringing some things together as well. So get ready for anything involved. Get ready to use your calculator, of course, when we do these. And let's see how it goes. Only 39 questions in total, but they could be quite a handful. So if you want to download this section, you can go to the description section down below and find the PDF of that. And you can also follow along and find each individual timestamp for the problem set up to problem number 39. If you want to find other things as well, you can go search within the playlist, my IM3 playlist. Without further ado, I'm going to go ahead and get started with the lecture portion. We're going to classify data sets, which to me means determine what kind of thing it is. Is it quadratic? Is it exponential? Is it logarithmic? Right, like that. Write exponential functions. We'll come up with what the equations are, I think, based off the information. It sounds like maybe doing it without a calculator, which is possible to do for perfect ones. And use technology to find certain models. So more in a scatterplot variety. Maybe they're not perfect models. That's ones where we can use those regression curves. We've seen them for linear and quadratic and things like that. Classifying data, we have analyzed finite differences of data with equally spaced inputs to determine polynomial functions. You know, first difference was linear, second difference was quadratic, third was cubic, fourth was quartic, things like that. For exponential data with equally spaced inputs, the outputs are multiplied by a constant factor. You might have heard for geometric sequences like a common ratio. I think we've seen some of these patterns already before, and I probably even used a problem and said, hey, I'll even come up with the equation for you. So we can get them if they form a constant ratio, what you're multiplying by from one number to the next, as long as the x's are equally spaced. So on part A, it says determine the type of function, or for parts A and B, determine the type of function represented by each table. On this one here, hopefully you're seeing this common multiple of 2 times 2 times 2 times 2 each time. So you can see that times 2. That is expressive of an exponential function. This is what exponential functions do. So this is an exponential function. They don't ask for the equation just yet. We can come up with it shortly. That's this one. Excuse me. Part B. I don't know. Let's see. Have them tell us. Okay, so we have a constant. We don't have a constant first or second difference, but we do have a constant third difference, so it's a cubic function. So it does look like they do want to differentiate between them to not just call everything exponential or logarithmic. Otherwise, it'll be very easy to determine. But that's what those two are there. This one clearly looks linear. Hopefully you can see that one there, subtracting 3 as x is increased by 10 each time. Okay, writing exponential functions. You know that 2 points determine a line. Similarly, 2 points determine an exponential curve. Yes, there's only one specific exponential curve that you can make out of 2 specific points, at least in this particular form, without any translations, using this. Now, they're going to use... Oh, they're not going to use this. Interesting. Okay. I was going to say they're going to use the elimination method like we would in systems of equations. You can use it, and I do want to show you it, but I'm going to follow along with their method as well with this, which is a fine one. They're using substitution method. Now, your 2 points that we have for these points for x and y are 1 and 6 and 3 and 54. That means in this system, or you can make a system by substituting 1 for x and 3 for x in 2 separate equations, and 6 for y and 54 for y in those particular equations, 1 with 6 and 3 with 54, and you can solve for a and b this way. Now, you first want to solve for b because the a is kind of just a constant value that works itself out in this way. If I can rewrite one of the equations where a equals blah, 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 so divide both sides by b, for example, this is what they did here. You can substitute that in for a in the other equation, and then you have one equation with one variable. This is a perfectly fine way to do this problem. So you have this here, b cubed over b is b squared, divide by 6, take the square root. There's no plus or minus 3. B can only be the positive number. Only b is greater than 0 in exponential functions. There's that. And then you can find a by doing 6 divided by 3, which is 2. Perfectly fine way. I have no problem with it. I'm probably going to do it more often than not. what I would generally teach, if you see another video where I do have this, or maybe your teachers would provide this as well, let's write the 54 equals AB cubed on top, just because it's a bigger number. It's easier to work off of. And 6 equals AB to the first power. In a system of equations, you've learned you can subtract both sides of an equation and add them. You can also multiply or divide. Now, division works in this case here. If you divide these sets, A divided by A is 1, B cubed over B to the first is B squared, and 54 over 6 is 9. So you get to that same setup of B cubed like that, plug it into an equation to solve for A. So any of that stuff is completely valid in order to find out what this is. You can see you get the same answer. Either or, I'll probably switch off. Now with A being 2 and B being 3, your equation is y equals 2 to the 3x power. Moving forward, data do not always show an exact exponential relationship. When the data is in a scatter plot, when data in a scatter plot show an approximately exponential relationship, you can model the data with an exponential function. So they give you information here. Store sells trampolines. I guess you got to buy trampolines somewhere, right? Maybe Amazon, but maybe the store. The table shows the numbers y of trampolines sold during the Xth year the store has been open. They're increasing them. They're increasing them. Write a function that models the data. So when you use the graphing calculator and you plot the points in, you want to see what your points look like they appear as. And to us, they appear exponential, I suppose. How can you tell exponential versus quadratic? I mean, quadratic doesn't have a constant common ratio, but then again, this doesn't necessarily either, right? It's a scatter plot, so there's no curve upward on the other side. Maybe I think we can trust, for the sake of the section, exponential model is safest to talk about here. It appears exponential to me. It appears that it curves down and maybe flattens out at some point. Anyway, let's come up with a model for this using regression. Oh, no, we're not using regression. I take it back. Choose any 2 points to write a model. Okay, I take this back. We're not using the graphing calculator just yet. We're going to plot the points and see what comes in. So not yet exponential regression. So we're choosing 2 points. Looks like they chose 112 and 4,36. Now, it looks like they're doing 2 points that were in the table, as opposed to, remember the linear regression when we would make a line that goes through? How can we make a curve that goes through and be sure that we did the best curve? I don't know. Maybe we could do that though. And okay, I went through that point, and maybe if I just went through that point as well. I guess you can just pick and choose, I suppose. I don't know. We're not drawing a curve of best fit. We're not too good at that necessarily. So pick 2 points, do the same thing that we did above to find your A and B so you can make your equation. Note that when we're doing these ones, we're making a general assumption, and I guess we'll have to live off it, but we're making a general assumption that we can do this without any translations, which means the asymptote is at y equals 0, which for a lot of these models will make sense that at some point should flatten out to 0 and not some other number, unless it's something different, right? Maybe we're talking about improving your mile time. And I used to tell this to one of my freshman students who ran cross country because she was in Algebra 2 at the time, and we learned the word asymptote already. And so I was telling her that, your running has an asymptote somewhere. Maybe it's at 5 minutes. Maybe it's at 4.5 minutes. Whatever it is, it's not at 0 minutes, right? We can't improve until then. So we flatten out somewhere. We can only get so fast at some point. She was buying it. She was all for it. But these ones here, I guess we're assuming there's no shift. So anyway, they're coming up with their equations here. Notice that they have the cube root of b for this number, but they substitute this here. They write the approximate versions of their numbers with a and b. Here's approximately cube root of b and 12 over cube root of 3 when they plug them in. So same kind of information that they did before. All right. Okay, so still not using the scatter plot, the graphing calculator yet here. A set of more than 2 points x, y fits in an exponential pattern if and only if the set of transformed points x, natural log of y fits a linear pattern. Okay, so yes. I just want to think about how I want to state this. There are, not that this is it because we're not changing our scale, right? Our scale is staying the same. There are some graphs that are useful. I'm trying to think of which ones, like in audio. I forget what it's called, like a wave spectrum thing, where you see all your wave frequencies, and they use what's called a logarithmic scale, where the frequencies from like 0 to 200 or even 0 to 1,000 or whatever are much wider, but then you go from 1,000 to like 40,000, it's like just as wide because they go on a logarithmic scale where as you increase, there's not as much space between the increases. so that you can see more relevant points better. And I think that's true for exponential functions here. Now keep in mind, they're taking natural logs of these things, so it's not the scale that's changing, it's the y values that are literally changing. Now this can be important because, exponential functions have a curve that you see it in our graphs a lot all the time. They take off so rapidly, so fast that you miss relevant data up here. If you can force it linear by taking the log of these values, or in this case natural log, by taking the log of these values and make it linear, then you can see the relevant data for it. Now, is that what we're doing? Is our goal to see relevant data or just come up with equations? We'll find out. But they're taking the natural log of their y values so they can fit a linear pattern within that. So let's take a look at their example with it. Here's an exponential curve, and here is their line that's represented by taking the natural log of these y values here. Let's see what their example looks like. Use the data from example 3, create a scatter plot of the data pairs. Was example 3 the trampoline one? Yes, it was. So use the trampoline stuff, create a scatter plot x comma natural log of y to show that an exponential model should be a good fit. So they're taking the natural log of their, I think it was 1 comma 12 and 4 comma 36. Well, the natural log of 12 is 2.48, natural log of 36 is 3.58. When we take natural logs of all these values, we can see that the data now fits something very linear. So that's a good argument to say that this kind of does look like an exponential function as a result of that. They said then write an exponential model for the data. Well, these ones are now natural log of the y values. I imagine that we could solve it like we would any other linear equation, but instead of using point slope form with y minus y1, we can use natural log of y minus natural log of y1. So in this scenario, these y's are natural logged. So our slopes, here we go. This is what I was looking for. So our slopes, the x's are not natural logged, only the y's are. We find the difference between the natural log of y's and the difference between the x's, and it creates a little slope. Given that this y is still natural logged, if you want to solve for, slope, y-intercept, things like that, we can get to this setup here. The natural log is by itself, at which case you can rewrite it in exponential form. Remember, natural log is log base e. That means e to this power equals y. So that's what they have here. You can raise e with the base for both sides being exponents like that. Cancel these out, have y, and then you have this. Now what they show next is another property, kind of written in reverse. We normally don't do it this way, but when you have a sum of two numbers inside an exponent, you can separate them with the same base and as a product, right? We know that, I don't know how to write it specifically, x to the m times x to the y equals x to the m plus y, right? Well, we're going this way. We're taking a sum and creating a sum of exponents and creating a product of your bases out of it. Now, why would you do that? Because we want to write this in exponential form. We want an a times b to the x power. So we want an a number to represent, well, not the constant, but the y-intercept, I guess, in this case. This is your a value, and this is your b value here. If you do e to the 0.35, we should get 1.42, and that's still raised to the x power. Now, last time, what was our answer last time? This is 8.41 times 1.42 to the x power. This is 8.32 times 1.44 to the x power. Bottom line is you're not going to get the exact same answer for these. Oh, by the way, which points did they choose? I don't even know. Which points did they choose here? They said, let's see, close to a line, find an exponential model by choosing any 2 points on the line. So they choose these ones. Looks like they still chose ones that were from your data set. I guess that's fine. All right, we'll choose ones from the data set. We'll do the slopes from there. Anyway, it's not going to be exact for both. We're doing rough approximations of everything we do, but they'll be good enough for what we do. And it just goes to show that they were close enough for them. They were very close together. Okay. Now using technology. Now we can use regression functions, exponential regression, logarithmic regression. We haven't seen any logarithm equations yet, by the way. You probably won't see them in the tables because logarithm equations require a constant increase in y as x increases by an exponential amount. We'll see if that's something that they compare. I don't know. I don't assume that we will be seeing that, but we'll see. But here, possibly we will. Use a graphing calculator to find an exponential model for the data in example 3. We just saw, the same example, trampoline one. So we're going to plug those points into that y2 and L1 and L2 lists, and then we can use exponential regression. That's within the stat calc menu. And then we can come up with those ones, and they'll give you some stuff here. R squared is always a number that we like to see, or R, the correlation coefficient, being extremely high, close to 1, where these end up being the A and B values here. So we can rewrite this equation, I guess, 8.46 times 1.42 to the x power. And there's that example. They say substitute 8 into each model to predict the number of trampolines sold in the 8th year. Our example 3 model, example 4 model, and regression model are here. Now regression should be closest because that's the one that's done through a computer. I don't know if that word's computationally or whatever. It's done through a computer, so this should be closest. Predictions are close for the regression model and the model in example 4 that use transformed points. These predictions are less than the prediction for the model in example 3. Are we supposed to actually make statements on these? I don't really know. All right, find a logarithmic model. Let's see what they want to say here. Oh, okay, so this is an example of where something's logarithmic. Notice how independent variable is changing by a varied amount while the y values, the dependent variable, is actually constant. The atmospheric pressure decreases with increasing altitude. At sea level, the average air pressure is 1 atmosphere, or that number. They're being very specific as to what that is. The table shows the pressures P in atmospheres at selected altitudes H in kilometers. So 5 kilometers up, this is the pressure in kilograms per square centimeter, etc., etc. Use a graphing calculator to find a logarithmic model. So they tell you it's going to be logarithmic. Of the form H equals A plus B times natural log of P that represent the data, estimate the altitude when the pressure is 0.5 atmosphere. So they did specifically state natural log. I do believe the calculator has a log regression and natural log regression. By log regression, that would probably be common log, unless they talk about different bases. I don't know. I haven't done it, at least not in a long time. So we're going to enter the data into there, right? L1 and L2, and then we use that natural log regression feature, and it gives you your numbers. So the A, this number is the 0.86. They're going to round these apparently. And then minus 6.45. I think there's a way to use the exact numbers. We've seen that before. We can use the vars, yvars, I think, function feature, and we can put those in. I got to check where it is. No. It's the regression equation feature. I'm going to find those for you when we plug them in. Anyway, we're going to substitute 0.75 into this thing for P, for pressure, to find what altitude that is. Looks like when you plug that in, you get about 2.7 kilometers. All right, that's the information for the lecture portion. Let's go ahead into the problem set, starting with questions 1 and 2 on vocabulary and core concept check. Let's see if I can answer these properly. Complete the sentence. Given a set of more than 2 data pairs x, y, you can decide whether a blank function fits the data well by making a scatter plot of the points x, natural log of y. If we're taking natural log of y and they make something linear with that, we're talking about an exponential function. Exponential function. What did I write? I wrote exponential. Exponential. I was thinking of function. Number 2, writing. Given a table of values, explain how you can determine whether an exponential function is a good model for a set. Oh, I thought they were going to say exponential, or this. Whether an exponential function is good for the set of data pairs x, y. We're looking for a common ratio between 2 y values. Given a constant difference between equally spaced x values, I think they kind of say, equally spaced x values, we are seeking a common ratio among the y values. Now, I don't know if they showed any that were a decay, but if you're dividing by 2, that's multiplying by 1/2. That's still a common ratio. So that would still, common multiplier, excuse me, that would still be an exponential function, but it would be through decay, not growth. That doesn't make it logarithmic, right? A decay function looks like this, where it kind of lowers toward an asymptote, mind you, like that. That's not the same thing as a logarithm curve, where a logarithm curve takes off maybe like this, and it has an asymptote right there. 2 totally different things. So it's still exponential in that case there. All right, so we'll see if we run into any of those, but we're going to start problems 3 through 39 in this problem set. Get all your stuff ready that we need. Let's see how this thing takes off. Start with numbers 3 through 6, where they determine the type of function represented by the table, and we have to explain our reasoning. Now, I think for the most part on these questions, we got to do a little bit of kind of trial and error, but do some educated guesses with them. Like maybe if you seek one immediately, go after it. Like a number 3, I'm seeing something for what it is, I believe. I'm seeing perhaps a common ratio, that if I multiply 1 by 4 and 4 by 4 and 16 by 4, etc., and then, hey, 0.25 times 4 happens to be the same thing here. So I'm multiplying these things by 4. I'm seeing that off the bat without testing common differences. And I think that's okay to do. If you see the thing for what it is, go for it. This represents an exponential function because it has a common ratio of 4. Multiplying the same thing. And I think these are intended to be perfect for whatever they are, not scattered. So, if it doesn't multiply by 4 each time, lay off the exponential sauce. You know what I mean? You're going to go and seek linear, quadratic, cubic, something like that. Maybe there are other instances. We'll see if square roots or something come into play. I don't know. By the way, the x's did increase by a constant amount of 3. Therefore, this was appropriate for it. Number 4. Let's copy and paste this one in as well. Let's see if we can see it for what it is. And I think I do. And this actually harkens back to what I was just talking about right before the problem set. These numbers decrease. That doesn't mean it can't be exponential. And I do believe this is exponential. You might say that you're dividing by 2. And I get it. You are dividing by 2. But does that make it non-exponential? No, it does not. These are divided by 2. But we want to say what we're multiplying by technically. Dividing by 2 is multiplying by 1/2, by 0.5. That's the number that you want to state here. That does indeed still make this exponential. Now you can see the 1/2 and 1/4 and stuff. I think we can agree that that is times 1/2 each time going from one to the next. And it is. And x's are increasing by 1 each time, so it works there. This is also exponential. The common ratio this time is 1/2. It's exponential decay, but it's an exponential function. So there's numbers 3 and 4. I don't think everything is going to be exponential, so expect something maybe different coming up soon. We got to test the other ones and make sure not everything's exponential. Number 5 does not appear exponential to me off the bat. For one, there's a first decrease in numbers immediately from 4 to 3, and then it increases after that. They're not going to do that. And if we're talking about being perfect in some sort of way, obviously it can't be linear either. Doesn't mean it can't be quadratic, cubic, quartic, something like that. So let's go off of first differences. And first differences will show, obviously not a constant set, -1, +4, +9, +14, and +19. 19. And then I think second differences will be constant here. We are adding 5 plus 5 each time. So given that you're adding 5 each time, that's a constant second difference. The constant second difference makes this a quadratic function. They didn't ask for the model to my knowledge. Yeah, just determine the type of function, just a classification. This is quadratic for a constant second difference. Notice, by the way, the x's are constantly increasing by 5. The constant difference, by the way, is 5. Number 6. One more copy-paste job. Let's see what's going on with this one. Also doesn't appear exponential or linear. Perhaps well, if you notice what happens, the x's go constant. It stays at 5 twice, which means it loses its decrease, but then it begins to decrease again. It increases and then it decreases again. Probably a cubic or a quintic. I mean, we'll see. It's probably an odd degree function, just not linear. So let's see what happens here. We're first subtracting, what's that, 56, and then 0. Whether you're adding or subtracting, it's 0. 8, hoorah, and then -32. I always mess these up, so sorry. -120. I always mess them up. I hope I didn't already mess up now. Adding 56 and 8. Subtracting 40. Subtracting 88. I think 88. Subtracting 48. 48 and 48. It must be cubic. Cubic. So we're going back to things from the previous chapter. Constant third difference of -48 makes it a cubic function. We're just going back and saying not everything that curves is exponential or a polynomial, right? As we learned some things along the way. First two are exponential for different reasons. Okay, numbers 7 through 16. Write an exponential function y equals ab to the x, whose graph passes through the given points. Now, I showed in the lecture, they showed in the lecture doing this by substitution. I'd like to probably go, the odd numbers I'll do substitution, the even numbers I'll do elimination. I showed elimination on them as well. Both work, both are valid. You can just kind of look at both and make your determination as to which one you prefer. I don't think I have a preference. I think they just both are what they are. Now, the form is y equals ab to the x. Keep this in mind. So we're going to set up a system. xy, so y equals ab to the x, and xy, y equals ab to the x. Okay. So what you first want to do is Generally, you want to solve for a, because a is always the linear factor. You see, b can be raised. It can be raised to the first power, but it can also be squared. And you look at number 8, it's only to the second and third power. So it's easier to just get a by itself as a common thread here, divide both sides by b. You get 3 over b. And then you can take this equation, substitute 3 over b for a in this scenario to have an equation with one variable in it. So 3 over b, your goal is to find b and a. So 3 over b times b squared. B squared divided by b is just b. So you now have, this is going to be messy looking, 12 equals 3b, so b equals 4. There are other ways to come up with these through logic. Hey, we went from 1 to 2. This went from 3 to 12. 1 to 2 is just an increase in x by 1, right? Exponential says x increases by 1. What's y doing? We're multiplying by 4, going from 3 to 12, right? Now we still have to find the a value, which in these cases tends to be the y-intercept, so when x equals 0. You can plug in 0 for x and solve, for these cases here, what have you, but you need your b value first. Where do I want to plug in? Let's do to the top equation. So b equals 4. We have 3 equals a times 4. Divide both sides by 4. A is 3/4. So you have a is 3/4. That's exactly what you would get if you divided by 4 here to get to 0. And so this equation is going to be y equals 3/4 times 4 to the x power. You could also turn 3/4 into 0.75, but there's the exact fraction. 3/4 times 4 to the x power is our equation. All right, number 8. I'll solve this one this time using elimination. So our 2 points are 2, 24 and 3, 144. Now there are other things we can speak on as far as how we believe the answer goes. I'm going to write this one first. I like to write the bigger ones on top when it comes to using elimination method. So this is my x and y. Y equals ab to the x power. And here, y equals ab to the x power. Now I show this in the lecture portion, but I'm basically going to do a division between these two things. You can divide things as long as they're equal to each other, divide both sides. A divided by a is 1. You're left with b cubed over b squared, which is b, and 144 divided by 24, which is 6. Totally makes sense for the problem, by the way, because from 2 to 3 is an increase in x by 1. From 24 to 144 is multiplying by 6. That's how exponential functions would work. So I'm going to solve for a. Let's maybe take this equation here, the smaller of the two. 24 equals a times 6 squared. You basically got to divide 2 reps of 6, or 36, from a. You got to divide by 6 to get to 1. X equals 1 and x equals 0 divided by again. So a is 24 over 36. This is 2/3. I dare not write this one as a decimal. So 2/3 for a. Our final equation is y equals 2/3 times 6 to the x power. That was the elimination method, and I'll continue it for the even problems. Odds, substitution, even, elimination. Number 9. Number 9, we have 3, 1 and 5, 4. You know what I should have done actually for the substitution one, and I'll do it this time. I'm sorry that I didn't do it the last time. I had an equation where a was by itself, and it said a equals. I totally should have plugged it into that b. So I'm going to use it this time. No worries. I got my xy, so 1 equals ab to the 3rd power, and xy, 4 equals ab to the 5th power. Let's get a by itself in one of the equations. I like this top one. So this is the one that, again, I'm going to go back to right here. A equals 1 over b cubed. I'm going to go back to this one. When I solve for b, let's say it's 2. I'm going to substitute, actually I think it is 2. I'm going to substitute 2 into here, and then we'll get our a value. So now we're going to first substitute 1 over b cubed into this equation, right? It has to go in the other one. 4 equals 1 over b cubed times b to the 5th. Let's solve for b given this. B to the 5th over b cubed is b squared. 4 equals b squared. Take the square root of both sides, you get b equals 2. That's what I was saying. I think b is 2, and there it is. Not plus or minus 2. You can't have negative b values. You can't have negative 0 or 1 as your b value in an exponential function. Otherwise, it's not exponential. Okay, as far as a goes, a equals, it's just arrows. Arrows everywhere. A is 1 over 2 cubed, which is 1/8. So as far as an entire equation goes, this will be y equals 1/8 or 0.125. But 1/8 times 2 to the x power. Of course, you can double check all of these. You can substitute 3 into here. You can see if it's multiplying by 2 each time to get to those sets, all that kind of stuff. And I'm trusting it. It's looking pretty good. Number 10. After number 10, I'm going to go faster on them. I'll stick to those strategies I was talking about, but I'll speed it up a little bit more. 327 and 5, comma 243. Let's substitute x, y. I'm going to use the bigger equations on top this time. You can always use bigger equations on top. It's kind of your choice. But I like to divide bigger from smaller. And I'd err to the side of making your exponents positive as opposed to making this thing a whole number. So always kind of make the x's bigger to begin with. So 27 equals ab to the third power. As we divide down these lists, the a's go bye-bye. In a way. B squared is here, and 27 times what is 243? I think it's 12. Wait, that doesn't make any sense. No, it's not 12. What is it? 81. It's 9. It's 9. I was thinking 27 times 4 is 81. That's a big my bad. Take the square root of both sides. You get b equals 3. Again, no plus or minus. Now we substitute in one of these equations. Here's the problem with elimination. A never got by itself yet, so I got to now do it here. So 27 equals a times 3 cubed, which is 27 equals 27a, which means a is 1. Now, you don't have to write 1 in your equation. We normally don't expect to see it in our equations. Instead of 1 times 3 to the x power, I'll just write 3 to the x power. I want you to know that that means a is 1 in the problem, but it doesn't mean we have to write it. All right, a little bit faster now. 1, 2, and 3, 4. Just kidding. 350. Good old substitution happens here. AB to the first power, or just AB. And then AB cubed. I'm going to get A by itself here. You get 2 over B, and it substitutes into this equation down here. We get 50 equals 2 over B times B cubed. B cubed over B is B squared, so 50 equals 2B squared. B squared is 25, so B equals 5. Now that we know B is 5, A must be 2/5, a direct substitution into that. Perfect. 2/5 is also 0.4. So our equation is y equals 2/5 times 5 to the x power. Now, I'm going to kind of keep stressing over and over that this is a procedure that it should make sense algebraically, and I really want to promote it algebraically. But if you forget what to do, let logic take hold and ask yourself what you're looking for. You're looking for the common multiple from 1x to the next. And you're also looking for the value of y when x equals 0 by dividing by that value all the way down until you actually land on 0 for x. So there are other ways you can absolutely do this that's not through these methods of substitution and elimination. All of it can be logical. Although I'm going to do elimination, let's think of this one logically together for a moment and see if it works out in our favor. For example, there's a point in between here, right? We go from 1 to 3, so there's a 2 in between. So we got to multiply 40 by something there and by something there to get 640. So we got to multiply by something twice, the same thing twice. The thing we multiply the same thing twice eventually is multiplying, what's 40 times what is 640? 16. So we got to multiply by something and by something to get 16. What times itself is 16? 4. So 4 must be my b value. What's my a value? It's the value of x, the value of y when x equals 0. So you got to divide 40 by 4 and you get 10. So I believe the equation is going to be y equals 10 times 4 to the x power. Now, we're doing all that work. When we do this stuff, we just write it out algebraically. So y equals ab to the x power, and y equals ab to the x power, to the first power. These are gone. You get 16 here, and you get that b squared, and b is 4. Once again, we're coming up with that number for the same reasons that we were here. It's the same reasons. Now, a times b, 40 equals 4 times a. You divide by that 4, and you get 10. And there is the equation that we have from that. That was elimination. Again, I don't know if you have a preference yet on which one you like more, substitution or elimination. I don't have a preference. I really don't. Number 13, we do have a negative in the way on x here. Will it make much of a change? We'll find out. 4, comma 0.31. That'll make a little bit of a change. All right, so y equals ab to the x power. And y equals ab to the x power. Very interesting. Let's still get a by itself. Remember that b to the negative first is 1 over b. That means we can say a divided by b, which might be a little nicer. This means a equals 10b. 10 times b, not divided by. It's not as icky looking. Doesn't really matter much once you substitute it into here. 0.31 equals 10b times b to the 5th. b to the first times, or b to the fourth times b to the first is b to the fifth. So this will become 0.31 equals 10 b to the fifth power. Divide by 10, you get b to the fifth equals 0.031. And take the fifth root of both sides, b is the fifth root of 0.031. If you think that's an exact answer, you got another thing coming. I don't believe that's an exact answer for a second. We will round it. We will round it for our final answer, but we need to use this exact number when we solve for a. Keep that in mind. The 10 times b, whatever. Of course, we're going to be rounding that one as well. But the fifth root, I'm going to my calculator. I'm going to type 0.031 raised to the 1/5 power, or 0.2 power you could do. And that's 0.499. I forget how many decimal places. I'm just going to say 0.50. I think they did 2 decimal places when they did these before. So it's around 0.5. Really, really close, but not exact. Because I believe 0.5 to the fifth power is 0.032. Right? I think that's what that is. Now a equals 10 times the fifth root of 0.031, which, look, that just means it's going to take this whole thing and it's going to shift it 1 decimal place over. So it's going to be 4.99. 4.99. That will be the extent to which I do a little bit of rounding on this question. Maybe if we want to round into the nearest whole number, it would be 5. So it's up to you. I'm going to do 2 decimal places, though. So y is 4.9. It's approximately. Times 0.50 to the x power. I can imagine saying 5 times 0.5 to the x power is nice as well, but then they could have given us a better number. So if they didn't want us to round, they could have done that. Number 14, I guess that's not the last question because we still have 15 and 16 to go. But number 14, see, it's questions like these where I would lean more on a method just because I don't want to get bogged down by icky numbers and thinking about what I have to do to go from one to the next. So it's absolutely going to make more sense to write the system and solve using a method. So I'm going to use elimination this time. And I'll probably use the calculator. When I divide these up, boom, boom, I'm going to get b cubed over here. And over here, oh, 4,096. I do know that. Those are powers of 4, 4 cubed, and shoot. I know it's something. 256. I want to do this in my head. Anyway, I want to do it in my head. I know it's something. Honestly, it might be 64 squared. So this number might be This number might be 64. 409.6 divided by 6.4. It is. It's 64. So this number is 64, and it's a perfect cube. So b is the cube root of 64, which is 4. Definitely no plus or minus here. It doesn't matter if we're talking about whether they have them or not. Cube roots, not plus or minus. Let's go to the 6.4. 6.4 equals a times 4 squared. 4 squared being 16. Let's divide by 16. This might be a clean. 64 divided by 16 is 4, so 6.4 divided by 16 should be 0.4. So a equals 0.4. That's exact. These are not approximated. So this will be y equals 0.4 times 4 to the x power, using the elimination. 15 and 16 are part of the same problem set. Excuse me. They're part of the same problem set, so I might have to copy this graph over. Now, I'm keen on doing this without those methods. We've done the methods 8 times, right? Let's look at them in a graph-based form if things are reliable to what we have, if it makes sense. Like, for example, I see other points in between, and if I see those points, I can use them. This y value, and I'm looking at the y values because the x's are going by 1, right? This y value is 1, this y value is 2, this y value is 4. From 0.5 to 1 to 2 to 4, clearly we're doubling. Our b value is 2. If you want to find the y-intercept as it's not exact, we are multiplying by 2 going this way, so we're dividing by 2 going this way. So a is 0.5 over 2, which is 0.25. I'm just going to write that straight up. So our equation is y equals 0.25, or 1/4, times 2 to the x power. If you have methods, go after them if they work out. That's mine. Number 16, do we have more of the same here? Somewhat. Not exact values, and in fact, decimals can be more of a turnoff for this. I can understand if you want to go for a system substitution or elimination. If so, pause this and check back and see how we do. But this one, for starters, I want you to recognize, guys, that this one is exponential decay. That means your b value is going to be some form of a fraction. Now we're multiplying, x is increasing just by 1. So we're multiplying 10.8 by something, your b value, to get 3.6. That's exactly what's happening here. Straight up. I'm not going to write anything else with there, but if you do enough work, you'll actually get there. You divide by that, and you're going to get, it looks like, I believe that's 1/3. I believe that's 1/3. So your b value is 1/3. We got to take 1/3 of 3.6 and 1/3 of that number to get what your y-intercept is. So a is 3.6 over 3 squared, 3.6 over 9. You're going to divide by 3 twice. 3.6 over 9 is, I don't know what. 36 over 9 is 4. So this is 0.4. Again, we've seen a 0.4 before. That should be 0.4 as an exact answer. So my equation, I believe, is y equals, and I don't like having a decimal and a fraction here, but I can't have the decimal here. So I can either write this as 2/5. Yeah, you know what? These are decimals. That's fine. So 0.4 times, this one has to be the 1/3, and the others are decimals, so we'll leave it. 0.4 times 1/3 to the x power. It works. Now, if I did talk on things with negatives, remember this would be b to the negative third and b to the negative second. You're going to have to play with those, through division, subtracting and negative is addition. You have b to the negative first if you use elimination, stuff like that. So just be wary, be mindful. All right. Let's go to number 17 and 18 on error analysis. In exercises 17 and 18, describe and correct the error and determine the type of function represented by the data. We're multiplying by 3. I agree. The x's are equally spaced. Outputs have a common ratio of 3, so data represents a linear function. No, it's an exponential function. Common ratio, a common ratio, which they're right. It does have a common ratio. Oh, by the way, there are going to be a lot of fireworks going off at some point here, I'm sure. A common ratio. This video may not be recorded the same time that you see it uploaded or that you're watching it. A common ratio represents an exponential function. And you might not hear the fireworks at all. I hope my microphone doesn't pick it up. That would be very annoying if you hear what I hear. So listen, that's the answer. That's the correction. It's not linear. Not linear. Linear is a common difference. Common first difference, by the way. That's number 17. They were right on everything else. Number 18, we have multiplying by 2. Outputs have a common ratio of 2, so the data represents an exponential function. I agree. Oh, they're not equally spaced, though. There's no 0 in between, and there's no 3 in between here. So there's not equal spacing of your x's to have this common ratio. Therefore, I mean, really, it's a nothing burger. There's nothing that I'm sure we can say for certain in what it is. The fact that we're skipping only a couple of numbers to make this happen. The x's are not equally spaced. Always. Which means this can't be an exponential function. Maybe that's the closest to what it is, but not exact. The r squared isn't 1, for example. But I don't think we have, there is no exact relationship to fit this data. There's no known exact relationship. I'm going to say there isn't one. I'm going to say that's the part that they're psyching out with, and we're going to go with that. I'm sorry, I was supposed to put number 18 right here. Now, if you want to do some sort of function, you can go to the calculator. So I'll say to find the closest, use the regression feature in the calculator among different types. Shoot, we might have to correct this. Among different types to come up with a function, to determine to classify the function. So I think we're going to have to. Without equal spacing, there's no exact one. But let's go to the calculator. Let's do those values. I got -2, -1, 1, 2, 4, and 3, 6, 12. Clearly not linear. Not linear. We stated not exponential from the thing, but it could be so closest to that. Let's find, this is your first instances of looking at exponential here. Oh, I need to turn diagnostic on. This is something every time my calculator resets, it turns off. So I need to turn this thing back on to see my r squared values, things like that. So let's redo that one. It's very good. It's very good for an exponential function. It's not perfect. Well, I want to check on things like quadratic and cubic and quartic. When I said it wasn't linear, I want to check on those other ones and see if anything's better. Quadratics here. 0.98 was the other one. This is 0.99. That's even higher. So it's even better quadratic than exponential. Let's check cubic. 0.993 stuff as well. Very good. Let's 0.99386. Let's check quartic. This is the last one I think I can really fit in here. Otherwise, I'm not going to worry about it. R squared is 1. Oh, it is a perfect function. It's a quartic. Oh. Well, here's the thing. We didn't have the numbers in between to determine what it was. So apparently, this is a quartic function. So, okay, time out. So this is a quartic. But see, we didn't have the numbers between some of the other ones. So this would have had some gaps. So it would have been really tough to do. So this equation, oh, we don't have to come up with the equation. But it's a quartic function. R squared is 1. R squared is 1 means it's a perfect quartic function. Very interesting that they could come up with something with exponential behavior among points that weren't fully spaced out, right? And still make it something else. So good thing we ran into that. Let me pause for a second. All right, I heard some louder fireworks popping off. I think they're just going to continue. There was one that just freaked me out somewhere near my street. So I'm just going to have to deal with it. We're going to have to deal with it. All right. Number 19, modeling with mathematics. The store sells motorized scooters. The table shows the numbers. The table shows the numbers Y of scooters sold during the Xth year that the store has been open. Write a function that models the data. So this is one where, so let's see example 3. If you remember example 3, that was the exponential one. It wasn't fully exponential. It was a scattered plot data thing, but we didn't also use the calculator. So this is a set where I'm feeling a little vulnerable because I'm trying to determine how to use the calculator, but how to not use the calculator, but do it. So here's what I think I'm going to do, because we might have to go back to this one, and they say use this one later and find the same stuff. So let's start with the calculator now. I'm not going to use the regression feature on the calculator, but I want to type the numbers in to see the curve and see that, number 1, it should be exponential. Number 2, that I can draw a curve through it, that I can estimate which points would work best for this sort of. So I have x values of 1 through 7. And yeah, when you look at these numbers, they're not exponential. Actually, from 9 to 14 to 19 is linear. That's plus 5 plus 5. But then it's plus 6, and then it's plus 12. And then it's plus 16, and then it's plus 18. So there's probably some form, whoopsie, I started writing these numbers. Hold on a second. 37, 53, 71. I started to say 12 and all that stuff. Okay, so what I'm going to do here is I'm going to turn stat plot on. I'm going to plot these points and I want to see them. I want to go from, well, I'm going to create a window range. Let's go from 0 to 10 is fine, and for y, let's go from 0 to 80. Let's see these points. So there are the points. Yeah, I buy the exponentiality in this one to the effect that if you want to draw a curve, go ahead. So, you know, I don't have graph paper to scale up to 100 like that. Could I done that? Yeah, maybe next time we do something like that I can. But now I'm one step ahead of a future problem that we might have to do with these ones. Now, can an exponential curve fit through this that you'd want to request? Remember, it's got to approach the asymptote as well. I don't know if you heard that pop from the fireworks there. But you got to do something that's kind of going through. And I said you probably aren't supposed to be drawing a curve through these points, whatever, but okay, that could be the curve that models this. Anyway, let's pick 2 points that we say goes through it. I'm going to say this one and this first one. Why not? So let's pick 2 points. I'm going to choose 1, 9, 1, 9, and the second to last one was 6, 53. Why not? We're going to write an exponential function through this using what we did before. This time, we definitely want to use that whole y equals ab to the x thing. So y equals ab to the x to the first power, and y equals ab to the x power. Now for this one, I can rewrite this as a equals 9 over b, so I can substitute it into this one here. 53 equals 9 over b, that's a 9 by the way, times b to the 6th power, which is 53 equals 9b to the 5th power. Divide both sides by 9. It's not a perfect value, unlike the ones that, of course, they had on theirs. 53 over 9, and so b is the 5th root of 53 over 9. That approximation is, and I don't know how they decided which points to choose for it. 5 point, okay, I got to take the 5th root of 5.8 repeating. 1.43 is my approximation for my values here for b. 1.43. Now my a value is based off my b. A is 9 over the 5th root of 53 over 9. So I have to take the exact one to do the rounding with. So I'm going to do 9 divided by my exact answer that I have. And I'm getting 6.31. So my equation I'm getting out of this is y equals 6.31 times 1.43 to the x power. Now, if this follows along like it did in the lecture stuff, maybe we get to use the exact same information and do it with the ones where we take natural logs of our values and then the ones where we use the exponential regression features. I don't know how close this equation is to an actual answer or not. We'll figure it out shortly. If the lecture thing goes by anything, then this is going to be the least accurate one compared to the others. Number 20, the table shows the number of Y visits to a website during the X month. Write a function that models the data, then use your model to predict the number of visits after 1 year. Were we supposed to predict something? Okay, we weren't supposed to predict anything there. All right, this one we're supposed to make a prediction on. I think this time I'm going to try and push for using an actual graph thing and plotting them. It's just Y scales totally have to change here. X will go from 1 through 10. That's great, but this is going to go up to 1,000. 1,000 here. This is 500, stuff like that. So I'm going to make my own. I'm going to man up here. This is 100. This is 100 right here, so 22 is about a fifth of the way. When X is 1, Y is 22 right there. When X is 2, Y is 39. That's getting closer to half, but not quite there yet. When X is 3, Y is 70, more than half. Halfway to 100, I should say. When X is 4, Y is 126, about 1 1/4. When X is 5, this is fine, about 2 1/4. When X is 6, we got 408, a little bit more than 400, just a smidge. When X is 7, we got 735, so 700, less than a half right there. So there's our curve. Okay, that's fine. It looks exponential, right? We probably should have done this the first time. I'm going to kind of rough out the idea of a curve that might go through there, though. I think any of these 2 points would do. You know, points that are maybe sometimes farther out are better for this stuff, so maybe the 2 farthest out would be best for it. I don't really know. Or numbers that would be cleaner with what we do, and I can't guarantee anything that'll be clean in what we do here. So let's do this again. This time I'll use elimination method to come up with the equation. Last time I did substitution. 2 farthest out points, is that too obvious? Let's go for it. Let's use 122. I mean, I drew the curve through however I drew it. 122, and let's use 7 and 735. Why not? Okay, so with this one, we'll have y equals ab to the x and y equals ab to the x. So through division, this becomes b to the 6th and 735 over 22. Is there any cleaning up that can do for us? None so whatsoever. No fraction reduction, no nothing. So 735 over 22, no exact decimal. So b is going to be the 6th root of 735 over 22. Now, approximated, that is, to 2 decimal places, that is 1.794. So 1.79. The a value is found by plugging in our exact b. So 22 equals a times our b. Man, I am hearing the rain of some fireworks stuff. Super apologies if you're hearing that and it's just not working. Maybe it serves as a little bit of ASMR. I have no idea. And if you can't hear it, fantastic. All right, 22 over this number is going to be 12 12.26. So this equation in full for me will be y equals 12.26 times 1.79 raised to the x power. So it doesn't look like we're taking our old data to come up with these unless they show them later in the problems. It looks like maybe they'll show them later in the problems when we do actual regression ones or whatever. All right, 21 to 24, determine whether the data show an exponential relationship, then write a function that models the data. It sounds like even if it doesn't make an exponential relationship, then we still write a function for it. So let's figure it out. First of all, we have to confirm that the x's have equal spacing, in which case they do here. We're adding 5 each time. We have to figure out if we're multiplying the same thing from 12 to 28, 20 to 76. And you go, how do we figure that out? 12 times what's 28? You do 28 divided by 12 to figure it out. 28 divided by 12, well, it should be multiplied by 7/3. So 28 divided by 12, I believe, is 7/3. But it's, yeah, right? So 2.3 repeating. How about 76 divided by 28? I'm doing these in the calculator, by the way. It's not the exact same thing. So it's not exponential. So exponential, no, at least not exactly. So let's go for finite differences. Let's see what's happening there. From the first set, we're adding 16, 48, 114, and 360. No, 260. And then for my next trick, for my next set, it says then write a function. Ooh, the x's are going by 5s though. That'll be important for when we do, if we're doing some polynomial thing that's not exponential. Okay, this is plus 32 plus 66 and plus 146. Am I not seeing something here? This isn't going to get me something that I want. I don't know if these are supposed to be exact. I'm erasing that because this is plus 34 and plus 80. And then I'm only going to have one number. So it's clearly not one of those. Even if it was, we'd have to use the regression feature in our calculator to get an exact function. It says determine whether the data show an exponential relationship. Maybe they're saying not exact. Maybe they're just stating do what we were doing before. So I'm going to go ahead and say yes. This was close enough. What I did, and I'm going to show you those two numbers that I did before. I did, wrong button. I did this divided by this and this divided by that. They're close. They're not exact, but I think when we're dividing these, we're within ballpark of saying it's got exponentiality in its wake. So 450 divided by 190 are showing these are there. I think we're doing the same thing as the word problems, guys, that it's scattered, it's nearabouts, it's not perfect. We're doing what we can, so we pick points. So is this exponential? It appears it's exponential. Otherwise, you can't come up with a function. So I'm just going to go with this. Let's choose 2 points on here. I'm going to choose 2 randos. Let's go with these two. So 6 and 28 and 11 and 76. So this is going to be y equals ab to the x and y equals ab to the x. Do a substitution here. We'll get 76 equals 28 over b to the 6th times b to the 11th. Here you have your 76 over 28. B to the 5th equals 76 over 28. You can divide them by 2. You get 38 over 14, which is 19 over 7. So 19 over 7 is the most I can reduce that to. So b is I don't think that'll matter. We're just doing this part anyway. So 19 over 7. Did you hear that? 5th root of that number. And we're getting 1.22 about. So there's the b value. Excuse me. Now the a value will have 22 28 over 1.22 to the 6th power. Now remember, there was an exact number there that I'm using. So I'm going to raise that exact number to the 6th power. And I'm going to do 28 divided by that. This is all in the calculator, by the way. And I'm getting about 8.45. 8.45. So there are a lot of different answers you can get based on the values that you choose. I'm going to go ahead and say this was exponential looking. So I'm going off of that one here. So 8.45 times 1.22 to the x power. Sorry on the beginning portion of this thing. It wasn't exactly exponential. I didn't know what they meant off that. They don't say see example, whatever, for me to know for sure. I thought they were supposed to be exact fits. It clearly wasn't one of the cubics, quadratics, anything like that. So I think that has an exponential appearance to it. Number 22. Honestly, I'd say the same thing on number 22. You're probably multiplying some things with equal spacing between these ones. Let's go to the calculator and check some of these out and see if they're decent numbers. This is just me guesstimating with tests here. I'm going to do 7 divided by 2, 24 divided by 7, 68 divided by 24, and 194 divided by 68. I know there's a big discrepancy between 3.5 and 2.8, but it's still within 1 when it comes to multiplier. And again, probably not the common difference realm, and even if it was, I don't see what kinds of equations we're coming up with without using the regression feature on our calculator, especially given the x's aren't equal spacing. When I'm looking at something like that, I'm seeing exponential. I'm seeing exponential. Is it perfect? No. Is it exponential? Sure. So number 22. And again, maybe we could look at the graph. Maybe we could plot the points and say, what does it look like on a graph? I'm not really in my scale ways right now for every single problem. So I'm just going to do some tests like that and kind of see how it looks. So number 22, I'd say it's also exponential. Choose 2 points. Let's try some with negatives this time. I'm going to go from -3 to 3 and just kind of go out that direction and see how things are looking. All right, so I'm going to use elimination method, and I get 68 equals AB cubed, and 2 equals AB to the -3rd. And in using elimination, we divide, A's go away. 3 minus -3 is 3 plus 3, which is 6. So we got B to the 6th here, and 34. And that'll give me B is the 6th root of 34. So 34 to the 1/6 power is the way I'm going to do it in my calculator. I'm getting 1.799, so around 1.80. And this all depends on the two numbers you choose, right? I chose that set, so it's all dependent. A, well, hold on. I don't have A by itself yet. 2, oh, let's use the top one. I don't want to use negative exponents. 2 equals A times 1.80 cubed. So A is 68 over 1.80 cubed, which is about, and I'm using my exact number, 1.799892164. Let's cube that, and let's do 68 divided by that number. I'm doing this all in my calculator, by the way. I'm getting 11.66. So as an answer, I'm going to be writing y equals 11.66 times 1.80 to the, not to the 3rd power, to the x power. To the x power. Okay, so as exponential as I feel I can make it, sure. Yep. Okay. All right, number 23. Have we been copying and pasting the tables? I think so. So x's have equal spacing on number 23. Y's, I don't know if this is exponential. Maybe. We're doing -8, -10, -6, -11. To go increase, decrease, -5, -5. I'm not loving that look for exponential, I'll be honest. Exponential is not about what you're subtracting, but the fact that we're subtracting more and then significantly less and significantly more again, that's not an indicator of exponential stuff. I know that here it kind of helps itself out later, but not from -8 to -5 with these gaps in between. This is not exponential. It's not exponential. In fact, I'd rather work linearly with this kind of stuff. It's kind of averaging like -7, -8, kind of like that in between as a whole. I'd rather do a linear equation with this. And if we do linear equation, let's use something off linear regression. I will make a graph out of this one. So with this one here, are these all positive? Yeah. Let's get into all positive realm on this guy. Scale the y. Well, scale both x and y by 10s. So this will be like 100 and 50 and 50 and 100 like that. So we'll get 0, 66, 50, 60, 66. Let's see if this looks linear to us. 10, 58. 20, 48. 30, 42. You might go, oh yeah, oh look, exponential. 40, 31. Oh, wait. So you see that? That's more of a linear basis there. 50, 26. And 60, 21. I'm not seeing the exponentiality on that. You might argue it's kind of curving off that way. I'm not seeing it. I'm not seeing it, guys. I'm seeing more of a linear, personally. I'm going to go with linear. So my line of best fit through that, probably looking something like that right there. Now, are there any points that I made this thing go through that I can work off of? Not really. Let's see. And remember, they don't have to be points on... They shouldn't be points from your data. They should be points that are on your line, if that makes sense. So if I extend my line enough, am I going through anything that looks good? Like I went through this one. I think that looks good. So I'm going to choose -5, or -50, I should say, comma 100. And then, does it go through any one of my points? I didn't really make it go through one of my points very well here. Huh. How about it kind of goes halfway here? Let's say 40, 35. 40, 35. I'm going to go with that, okay? So let's go. Slope is y2 minus y1 over x2 minus x1 plus 50, I guess. So that's -65 over 90. At least those are kind of decent numbers that I can write out. Divide them by 5. That's -13 over 18. I don't know. We've been doing things with decimals. Maybe I can write that into a decimal form as well. As far as y-intercept goes, we can substitute in point slope form. Let's choose 40 and 35 for that. We can do y minus y1 equals m times x minus x1. 40 and 35, right? Okay. And y minus 35 equals -13/18 plus, what's 13? That's 40 over, hold on. 13 times 40 over 18 as a reduced fraction. I'm probably going to write the decimal versions of these. The other ones have been decimals, but 260 over 9 for now. 260 over 9. This has an x, by the way. Add 35 over, you get y equals, I'm going to round all this stuff, -13 over 18 for me is around -7 point, or -0.72, -0.72x plus, and I got to do 269ths plus 35. And I'm getting 63.88 plus 63.89, I should say, like that. So that's about it for the linear regression thing. It's whatever. It looks like it's hitting the 63 number there as well. And I guessed on that other number that I put in. So I'm going to take it for what it is. Looking good, looking good. All right, number 24. Didn't love, I don't love this block of problems because they're not exact. They don't say whether or not to use a calculator, and it's a little bit of a mess for me. This set here, subtract 6, -5, -6, -5, -3, -3, -2. At least it's losing a decrease over time. I can buy exponentiality here, assuming x's go by a constant amount, which they are. They're going by 7. I'm going to believe exponentiality here because it's losing stuff. It clearly won't be linear, and we haven't seen any instances where we can do polynomial things on this. So I'm going to trust exponential for this one. I'm seeing it. I'm seeing it. Let's do numbers that'll work well through division or something. Of course, none of these will. Let's just do the far ends. Why not? So on the far ends here, I feel like the far ends are the ones that kind of make the most out of what you have. So y equals ab to the x and y equals ab to the x. Divide here. I'm going to use elimination method here. Divide here, and you get b to the 35th. Make that positive. And this is 6 over 25. Crazy number. We're about to take the 5th root of this. Now, the 35th root of this. Now, here's the thing. It's not going to be very small. It's going to get very close to 1. It might even round to 1, which is going to be awkward and bad if it is. But b is the 35th root. Hopefully, it's at least 0.99 of 6 over 25. Let's see how this one will pan out. 6 over 25 raised to the 1. Oh, and that's 0.24. That's an exact number. Oh, duh. 1 over 35th power. Okay, 0.96, and it's 0.9600. So I'm going to take that 0.96 answer and like take it to the grave with me. I like that number as an approximation. It's pretty good. It's pretty good. And that I think that's reasonable for what we're talking about here as well. The a value, 6 equals a times 0.96 to the 15th power. Remember, I have the exact answer on here. So a is 6 over 0.96 to the 15th power, which is about 6 over that. 11.06. So I'm getting an equation of y equals 11.06 times 0.96 to the x power, like that. Now I'm going to trust that. That's looking pretty good. It's decreasing, but not by a significant amount each time. It's not this super sharp one. So it'd be very close to 1, but also have decay. Seems to really hold up. Okay, number 25, modeling with mathematics. Your visual near point is the closest point at which your eyes can see an object distinctly. The diagram shows the near point y in centimeters at age x in years. Create a scatter plot of the data pairs x. Sorry, I started to think about, because I saw this, I started to think, did they want us to do that for these problems? I don't think so. I think since they're saying example 4, this is our first time we're using natural log. So create a scatter plot of the data pairs x, natural log y, to show that an exponential model should be a good fit for the original data pairs x, y. Then write an exponential model for the original data. So x is age, y is near point. So our original information is for x, y going to be age 20, 30, 40, 50, 60. I'm actually going to copy and paste this table because I'm going to do it once with y and once with natural log of y. I want the numbers to be right there for me. So here's x, y, and then we're going to have x natural log of y after. All right, the y values initially are 12. These are centimeters, 15, 25, 40, and 100. Now, if we take the natural log of these numbers, we're going to have natural log of 12, which is, I guess we round these, 2.48. Natural log of 15, 2.71. Natural log, are we supposed to use a calculator? I don't think so. Natural log of, and we for natural log, yes, but not for the whole thing, right? Natural log of 25 is 3.22. Oh, the scaling for which I'll have to go here. Natural log of 40, 3.69. 369. Natural log of, not 60, 100, which is not 2, 4.61. Okay. As far as differences go, I don't know. Let's see. Do we have to draw it, or do we just come up with the differences? I'm kind of an either or on this one here. Should we use the tall? Maybe I can scale this differently if I use the tall graph. I don't know if you'll be able to see this all together, though. Let's see. Can I take it and shrink this a little bit? Take it, shrink it a little bit. That's a little too much. All right, can you see that together? I think so. All right. 15. Sorry, I have to think about this stuff here. If every 5 of these is I'm thinking about what I want my scales to be here. Maybe we'll go back. Let's get rid of this. Let's go with the squared graph. I'm still keen on looking at the differences of them, but okay. With the squared graph, I'm gonna make every two of them be a 1. So this will be 1, 2, 3, 4, 5, like that. The x's will go by tens, so this is 50 and 100. So we have 20, comma 2.48. That's really close to 2.5, so like that. There's a point. 30, comma 2.71. Remember, these are the natural log things, so around there. 40, comma 3.22. Ooh, that shoots up a little bit. 50, comma 3.69. And 60, comma 4.61. I mean, it kind of looks exponential again. Well, it doesn't curve back down to the bottom, but if I were to do something linear with that, it's not perfect linearity. I'm gonna go ahead and state that right now. There's not perfect linearity among those. I'd say the 2.71 could probably be a little bit higher up. Oh, maybe not that high up. Maybe maybe it's where it's supposed to be. Anyway, we still come up with the natural log ones. They said show that it would be good for the data pairs. That's sort of. I don't know if I love a line through that thing, but that's the idea, right? We want to make a line through this thing with a slope. Line's not my favorite answer for this one. I wish they did a better thing here, because we want to show that the natural log ones make a good linear relationship, and I can't say for sure that it is, right? I'm not saying that it is in any sort of certainty, but I'm going to kind of try and go through these points in such a way that it's kind of hitting there with line of best fit. So if you believe that something like that can work out, then fine. If that does, then let's find some points that we can say this thing goes through to create an equation out of it. I'm just going to go far out both directions. So this one, honestly, my rise and my run seems to stay underneath those points so perfectly. It seems like I'm rising 0.5 and I'm running 10. It looks like my slope here is a perfect like 1/1, but the scale for 1/1 is up 0.5 over 10. My slope is 0.5 over 10, which is to say that's my natural log of y over x. Okay, just keep that in mind when we're doing these slopes here. So 0.5 over 10 is also 1/20th. So my lny minus lny1, I got to choose a point that's on this graph. That's the only thing. I got to choose a point that's on this graph. I can't get one that I feel that I like the most. How about 30, comma 2.8? So 2.8 equals 1/20th x minus 30. Like that. So natural log of y equals 1/20th x minus 30 over 20 is 1.5, and we're adding 2.8 to that. So this is, did you hear that? So this is natural log of y equals, okay, I'm going to write this as 0.05 again, as 0.05. I'm not going to write 1/20th. 0.05x plus 1.3. I'm going to raise these with e as my base, and now this will become y equals, and I'm going to write e to the 1.3 first, and this is times e to the 0.05 to the x power. If you understand what's going on there, there's a sum of the two exponents, which represents a product of this base, and I wrote this one first because it's going to represent a constant value for us. I need to figure out what e to the 1.3 power is. E to the 1.3, I'm getting about 3.67. So my equation is going to be 3.67 times, and now I need to do e to the 0.05. 1.05 is my number times 1.05 to the x power. So that's going to be my equation for this in exponential form. Using some stuff. All right. Modeling with linear data, with exponential data, man. It's tough. We haven't even done logarithmic data, technically. Number 26, use the data from exercise 19, create a scatter plot of the data pairs, x natural log y to show, then write an exponential model for the data. So these ones, and sorry, I started looking at the questions below it to see if we're using regression yet. I need to actually see, give me 1 second before I do this problem. I want to see when we're actually using, oh, here we go, use a graphing calculator, so that's probably not till later. We got to do a lot with these ones first, and it's kind of by hand. It's a little tricky here. So exercise 19. Oh, that was this one. Okay, so let's get the numbers out from it. That was this guy here. What's up, guy? All right, exercise 19 is these numbers. We got to do natural log of these y values. Now, we had an equation before that was 6.31 times 1.43 to the x power. I'd love to compare what I get here with what I got then. 6.31 times 1.43 to the x power. I wrote y old. Yold. I want to see what we get next here. So we're going to use natural y. Oh, where's my question? Create a scatter plot to show an exponential model should be a good fit. All right, so we got to, hey, we got to do this. This is how it works, man. So I'm going to write a new column, natural log of y. Let's see how it goes. We'll do natural log of 9, 14, and 19. All right, my first three sets, 2.197, so 2.20, 2.64, 2.94, natural log of 25, 37, 53, and 71. These numbers I'm getting 3.22, 3.61, 3.97, and 4.26. Okay. I think I want similar scaling to what I had last time. Let's shrink this up again a little bit. I'm going to bring in graph paper. No, that's not graph paper. I'm going to bring in graph paper. I think these problems are just going to go slowly, guys. There's nothing else I can do about it. 5, 4, 3, 2, 1. Apologies for fireworks. X's can go by ones here. That's fine. All right. I got 1 comma. Oh, I'm sorry. Y's aren't going. Oh, yes, they are. Natural log. Natural log. We got to ignore these Y's here. Okay. 1 comma 2.20. That's 2.5. So 2 comma 2.64. 3 comma 2.94, 4 comma 3.22, 5 comma 3.61, 6 comma 3.97, 7 comma 4.26. That looks very linear. I dig it. I'm going to work with that one. I feel it. Let's do our best line that we can go through like that. Oh, let's go up a little bit. I think I lost some of its fit. Looks pretty good. Looks pretty good. Points that it goes through. Do I like that one more? Or I think I like this bottom one a lot. It's a weird one, but I always like to choose points that are kind of out there, literally. negative 10 comma negative 3. It's actually not negative 3. It's negative 1.5. Negative 10 comma negative 1.5. And then I like my own point that it's on, although I won't like the decimal things that I do with it with. It was this one here. I don't want to choose 5 comma 3.61 if I don't have to. How about we just go far out to this one here? As far out as possible will kind of be nice. So this is 9. This is 9 comma 5. All right. So let's do those ones, and let's write an exponential model, and let's see if it's close to this one, if, whatever, something like that. All right, so our slope, natural log of y2 minus natural log of y1, 5 minus negative 1.5, over x2 minus x1, 9 minus negative 10. So this is 6.5 over 19, which is very close to 1/3. I wonder if there's a better fraction than just 65 over 19. 13 over 38. The decimal's kind of weird. I'm going to write 13 over 38 to begin with. Eventually, I'm going to do the rounding, and this rounding is going to be 0.34. So I'm going to write 0.34 as the rounding for that slope. Remember, we're going to do e to this power eventually. So our equation is now natural log of y minus natural log of y1. I'll use 5 equals, and I'm just going to write 0.34 here. Don't worry, I have the exact answer there, of x minus 9. And I have to do a distribution as I add 5 over. Natural log of y equals 0.34x. Remember, I have another number minus, and I have my exact number here, times 9, 3.08, and then plus this 5. What is that? 1.92? I want to make sure. All right, yeah, 1.92. All right, so we're going to raise e with the e powers here, so that'll be y equals, and I'm going to do e to the 1.92, that number, times e to the 0.34 to the x power. Let's see how close it is to these numbers here, 6.31 and 1.43. So e to this 1.92, and again, I have an exact answer here still, e raised to that number, I'm getting around 6.83. So not quite the same. 6.83 times, and then e to the 0.34. Was that 13 over 38? It was. So e to the 13 over 38 power. And I'm getting 1.41. All right, how close was this to that? 6.83 times 1.41? 6.31 times 1.43. Pretty close. Pretty close. The A is a little different, and I don't know which answer I trust more. There it is. Okay. Numbers 27 to 30. Create a scatter plot of the points to determine whether an exponential model fits the data. If so, find an exponential model for the data. At this point, I'm really sitting here wondering if I'm supposed to do this for each problem. And I guess so. This is just the worst, guys. Hey, if you're assigned these problems, then welcome. I'm gonna copy paste their table and just keep at it. Let's hope it isn't exponential. You know what? This is totally exponential. Guys, take a look at these numbers. It's times 2 each time. Of course this one's exponential. I mean, I want to write an answer without having to do this. So, but we should see also exact linearity. I think that's the point. We should see exact linearity on these ones here. So I expect nothing less than being able to do that. The problem is, do I plot my points well enough? So natural log of y, we need natural log of 18, natural log of 36, 72, 144, and 288. So for the first 4, I'm getting, and these are rounded, 2.89. I think that's part of the problem. These are rounded, right? 3.58, 4.28, 4.97, and natural log of 288, 5.66. Okay, so let's get it started. Let's go to, whoops, I need graph paper. This is one I feel I cannot change the scales on quite as quite as much. And change the x scales. 1, 2, 3, 4, 5. I'll just leave them. We'll just leave them. We'll have to just go microscopically within here if that's okay. 1, 2.89, 2, 3.58, 3, 4.28, 4, let's see, 8, 9. I don't know if that's high enough. 4.28, 4, 4.97. Wait, what am I doing? 3.58. That's not 3.58 right here. What am I doing? Let me redo that. I think the first one was right. After that, I kind of messed up. So let me do that again. 2.89. I think I was going by my 2's again. 3.58's about right here. All right, 4.28 would be about right here. Yeah, I was still thinking of my scaling by 2's. I'm sorry. My first one was right. After that, I was changing my scales. 4.97 and then 5.66. Very linear looking. They should be linear, right? So I should be able to go through these points, you know, like that just fine. My problem is I don't know exact scaling of those, so I was doing the best I could. Drawing a line through those best I could as well. And I don't know if I want to choose those exact points because they are still rounded values, not exact. So I want to choose what I would find to be exact based off this. 0.66 should probably be a little bit higher, but even the 0.97, maybe if I went down one, over one. All right, I'm really going through the 0.02 pretty well. So I'm going to use that one. And I'd say it's going pretty well through 4, 5. All right, so I'm going to use those two numbers. So let's do slope is 5 minus 2 over 4 minus 0, so 3/4. Remember, these are natural log bits. So let's choose 0, 2 as our set here. Y minus, or natural log of y, minus y1 equals, oh, wait, if the y-intercept is 2, then we can just use that. So let's use natural log of y equals mx plus b, 3/4 x plus 2, like that. We'll raise these as exponents with e as your base, and we'll get y equals, we'll do e squared times e to the 3/4 to the x power. E to the 3/4 is 0.75, right? So I could say 0.75. Either way, we're going to compute these two. So e squared, well, 7.4, but I'll still write it out. E squared, 7.389, so 7.39 times e to the 3/4, e to the 0.75, 2.12 to the x power. Now, if this was done exactly right, it should have been a 2, right? It should have been 2. So maybe I didn't get these ones perfectly with that because it looks like they're multiplying exactly by 2 each time. So sorry that I didn't get the exact ones from there. I tried to work it. It's fine. It's fine. All right, let's go to number 28. We have to do the same thing. Same thing on all these. So common difference between the x's are, yes, there we go. These scales are crazy. I think at this point for me, guys, I'm going to do the regression on my own, but I'm going to type these into the calculator so I can get a better scale. Because what I'm having trouble with right now is the idea of the scaling of them. I'm still going to come up with the information, the table values, all that kind of stuff, but it's the scaling of my graphs and plotting those to measure that I don't think are working very well. And I apologize if that's what you're relying on for me with these ones. I'm going to work off of it in a different way. I think I'm adding unnecessary time to this one for questions that I think we're repeating over and over in an almost redundant way when, I don't know, I'm not book shaming here, but I am stating that we've already done this kind of problem, and I can't see where we're going with it that's any different, honestly. So for me, the problem is scaling of graphs that's taking up more time than I can really work off of. You saw last time I screwed up in plotting them, which is my fault. I'm just stating that this is where fireworks going off and stuff like that, it's tough for me to work off what it is. So natural log of 92.7 and natural log of 280.9. I mean, seriously? 280.9. So here, 4.53 and 5.64. Okay, what I'm going to do is I'm going to go to the calculator. I've been here. But I'm going to go to the calculator. I'm going to put these numbers in here for x and natural log of y, and I'll zoom fit these guys. 1, 4, 7, 10, 13. Or zoom stat these guys. 1.19, 2.31, 3.42, 4.53, and 5.64. Okay, so I'm going to graph and zoom stat, that's option 9, and it will get these points here. Now I'll draw my own line. I'll recognize this scale. Actually, we probably have to go based off of a decent scale for them. It looks like these numbers work very well. See, that's their scale. Let's go from 0 to 15 on x, and let's go from 0 to 300 on y. The only problem with this is I don't know which 2 points I want to choose. Oh, not 0 to 300. I'm sorry, 0 to 6. I forgot we're choosing the natural log of y values, not the y values. All right, 0 to 6. Okay. All right, there are my 5 points. Let's see if I can do anything better with this or not. The only reason I might not be able to is because there are no grid lines on the graph. So when it comes to me choosing points, I might just have to choose points on there. And I think the book might have even chosen points that are on these. It's pretty linear, after all. That looks pretty good. In fact, these might be multiplying by the same thing over and over. I never bothered checking. So if they look pretty linear, and I agree they do, we can choose any 2 points. I'd like to choose the 2 furthest points out, and I'll choose the ones that are actually on here. Remember, these are rounded numbers, though. That's 1.19 rounded and 5.64 rounded. So I'm going to make my slope equal to 5.64 minus 1.19 over 13 minus 1. So going back to the calculator for that, 5.64 minus 1. That's 4.45 over 12. There's weirder fractions than that, so I'm just going to kind of leave that fraction out there. It's around 0.37. Okay. Natural log of y minus, let's use 1.19. 1.19 equals the 0.37 number times x minus 1. So natural log of y will equal 0.37x minus 0.37 plus 1.19. I guess I'm not really using any rounded values anymore except for my slope one, 4.45 over 12. So let's see. Let's do that number times, hold on. Okay. So this number, I have 0.37x minus 0.819. I'm sorry, 0.82. 0.82. We're going to do these with e as our base. So this is y equals, and I'm going to do e to the 0.82 power times e to the 0.37 power to the x power. So let's do e to the first guy, and that is 2.27 times, let's do e to our slope. I'm going to type 4.45 over 12 because I have the exact one there. I'm trying to use some exact ones out of our approximated. So this is 1.45 to the x power. So that's what I'm getting out of that one. It looked like it was a pretty good pretty good thing going. I like it. Okay, number 29. X is increased by 7. So good start. Let's check out those y's in natural log form. Part of this is filling the dead air in what I say. I don't know if it matters that we have a conversation like, hey, how's it going? But I'm trying to come up with other things to state on these, and I don't know what they are. We still have 10 more problems to do after this question. I'm doing natural logs right now. Hold please. All right, the first three I computed. I have 2.28, 2.50, and 2.72. These have an exact difference of 0.22 each time. Is the next one 2.94? Is the next one 2.94? By the way, I don't know if the last one's had a constant difference either. This one I can tell. Natural log of 19. 2.94, 2.94. 2.94. It's rounded to 2.94, but it's 2.94. And is the last one 3.16? Maybe it'll go up to 3.17. Natural log of 23.8. It rounds up to 3.17. So clearly it has linearity. I'm going to state that. It clearly shows linearity. The difference between these two on each of them is 0.22 rounded. Everything's rounded on here. In fact, when I go to the calculator to show you this stuff, those are the numbers we're getting. So 3.17 is the rounding, 2.94 is rounded. So let's change these ones up. To these numbers here. Maybe I'm allowed to do the exact, oh, it won't matter because I have, I'm using this by hand afterward anyway. Whoa. Oh, whoa, whoa. That's why you have to look at your screen, Mr. Robinson. What are you doing? Let's do that again. Actually, I just have to delete some. 2.28 is the first one. There we go. Okay. So let's fit these ones. Let's go from negative 15 to 15 on X, and let's go from 0 to 4 on Y. All right. Oh, let's go from negative 15 to 16 on X. Negative 16 to 16. Multiples of 4, shall we? There we go. Okay. Very, very linear, sir. Very, very linear, sir. It looks like it works out to choose the endpoints pretty well. And I can see the linearity of this one here. I hope you can as well. But it seems to always work out, choose those endpoints for it. So as long as it appears linear, you can choose any 2 points to work out. And you know what? This will actually work out for the 2 endpoints here because when I do this... Oh, I'm sorry. It's these two numbers, huh? Darn it. Are there any better ones? I don't know. Not really. Okay. So slope. We get to do 3.17 minus 2.28, all divided by 15 minus negative 13. I don't want to get that wrong. Plus, I need the number anyway. Minus 2.28. 0.89. So 0.89 all over 28. Or 89 over 2800, of course. The rounded value is 0.03. Obviously, I'm going to be using something different ultimately. But y, natural log of y minus, what's a better y1? I guess we'll use 3.17. 3.17 equals m times x minus x1. All right. Add 3.17 over, distribute the 0.03. Oh, what is that number? 0.45? 0.45? 0.03. Well, I have an exact number I got to use anyway. Times 15.47. I guess it is. I guess it does have a rounded thing to it. So actually, the actual number, what I'm distributing here, rounds better to actually 0.48 instead of 0.45. Plus 3.17. See, that's the problem with using rounded values. That's why I'm using exact ones within here. Maybe I should keep hitting natural log of those numbers instead of just keep using the rounded. So because I am rounding some things early, right? That's part of the issue, but whatever. We're getting close enough. So natural log of y equals 0.03x plus 2.69 is what actually is appearing there. So e to these powers here, right? So y equals e to the 0.03x plus 2.69, or y equals e to the 2.69 times e to the 0.03 raised to the x power. E to the first value is around 14.78. So y equals 14.78 times, now e to the, what was my number? 89 over 2600? 89 over 2800. E to the 1.03 to the x times 1.03 to the x power. Okay. All right, that's my number 29. Let's go to number 30. Number 30, we have natural logs going on here. Common difference of 3 on x, okay. And then let's natural log these ones. Natural log of y. Okay. 1.4. 5.32. That was a big jump. And then a small jump, 6.41. Oh, this might not be good. Let's see some of these numbers. Okay, 0.34 is this natural log, and then 0.51, 1.67, 1.85. I don't think this is going to be a good linear function. And then 2.08. So this jumps up 0.17, then it jumps up 1.16, and then 0.18 and 0.23. I mean, these are fine. These are fine. Not here. That jump is substantial. That is off. There is no way that that's going to make a linear function. I don't know if I want to type them in to show you for sure, but there's no way this does. So 0 minus 8. It did say make a scatter plot, so I guess I still have to do that. 0 minus 5, 0 minus 2. Sorry, let me show you in the calculator what I'm doing now. I'm typing these ones in, and then 1, and 4, and then... Okay. Let's just zoom stat these ones. Yeah, no, not linear. Not linear. Therefore, if the natural log one's not linear, then this one's not exponential. So, not happening. Like I said, those are linear in themselves. Those, any 2 points make a straight line right there. And it also fits with the other data, but not exponential. We're not doing this. Not coming up with a model. Probably a good thing time-wise. Okay. All right, number 31, using tools. Use a graphing calculator to find an exponential model for the data in exercise 19. Then use the model to predict the number of motorized scooters sold in the 10th year. So now let's actually figure out which model fit best if either of the models are even good. We use this information here. I believe this was the set. And we have two other equations. I'll compare to them in a bit. Let me just kind of copy all this stuff down. This time we actually get to use the regression model thing. I don't need the natural log things. We're just going to use the regression model as it is. So get that exponential regression for this stuff. Let me get the other equations. 6.31 times 1.43 to the x power. Remember that number. Where was the other equation where we did this one? Oh, it's right here. 6.31 times 1.4. No. Copy. Paste. Okay. All right. Here was the first equation. Here's the second equation. This was earlier problems. I think problem 19 and like 26 or something like that. All right, let's do this again. We're going to go to the graphing calculator for this one. We'll type in those numbers. We will use exponential regression this time. So here they come. 1, 2, 3, 4, 5, 6, 7. True exponential modeling at its finest. This is trampolines, right? Or was that the lecture portion that had trampolines? All right, let's use exponential regression for this one. And our best equation for this will be, it's a 0.997 thing. So 6.70 times 1.41 to the x power. So here is the best one, which matches, I guess, more closely with 2. That's the one that matches more closely. Anyway, I'm boxing this one to say this is the actual exponential regression one. Now, we're going to use that equation to predict the number of motorized scooters sold in the 10th year. I believe x was the independent variable 10. So this is where we can actually put this equation into y equals if we go to, was it stat? Shoot, I can't remember where to go. VARs statistics, EQ, regression EQ. Come up with use the regression equation that we have there. That's the exact one. We can even see this one on a graph if we do fit to these points. Here's the curve that best goes through them. It's like the one I drew, right? I just, whatever. But there's the curve that best goes through those points. Anyway, let's find this out for the 10th year. So I'm going to ask in the table for x equals 10. And we'll get about 201 scooters. Year 10 is 201 scooters. Okay. So that's just where I'm writing that answer there. Hope that that's okay when we're doing that. Okay. Oh, I don't need to move on to that one. I can still fit down here. Number 32. Using tools. Hopefully that means the calculator. A doctor measures an astronaut's pulse rate y in beats per minute at various times x in minutes after the astronaut has finished exercising. The results are shown in the table. Use a graphing calculator to find an exponential model for the data, then use the model to predict the astronaut's pulse rate after 16 minutes. So no different from what we did before. We're just not comparing to old equations. I don't know if they asked us to compare. I just wanted to test the validity of them, and that looks pretty good. That looks pretty good. So here we're just going to do the same thing as far as substitution, or not substitution, but entering our values, right? That's not going to change. So very much like the last problem we just did. So in our calculator, we can enter in numbers and stuff. What'd you do today? Numbers and stuff. It's going to have a decay based on what you see there. We're going to use the exponential regression. Oh, I can just re-enter here. Exponential regression equation. Not that perfect. It's not that perfect. So let's see what it looks like on the graph. It looks good. Oh, I didn't make the equation yet. Hold on a second. Hold on. VARs, statistics, EQ, regression EQ. Okay, let's see it again. That's the best regression equation they could come up with there, actually. And you're like, well, why didn't they just draw it through that? Because then it doesn't approach the horizontal asymptote. So you can see that's their curve of best fit they can do with that. This one clearly has a different kind of asymptote going for it. If you wanted some sort of plus k value, you could make a much better equation. This curve is only so good, right? It can only be so good for this. So this extrapolation won't be that on point. It's just the nature of the beast. Anyway, when it comes to equation, I didn't write it yet. So our equation is going to be y equals 153.07 times 0.93 to the x power. So y equals 153.07 times 0.93 to the x power. So let's substitute 16 into here. And that's where I'm going to use the calculator again. So I have my equation entered into here. I'm going to go to my table. I'm going to enter 16 into here. And we're getting around 51.5 beats per minute. I don't think we capitalize all of them, but that's okay. That's what we're talking about, right? Heart rate, beats per minute. I think it's lowercase. I feel bad. Not knowing my science and my medicine. Yeah, it's not the best as far as what the model's not the best. Still works. Oh, sorry, it is the best. It's just, it doesn't have that shift. All right, using tools. An object at a temperature of 160 degrees Celsius is removed from a furnace and placed in a room at 20 degrees Celsius. Oh, this reminds me of the Newton's thing. The table shows the temperatures D in degrees Celsius at select times T in hours after the object was removed from the furnace. Use a graphing calculator to find a logarithmic model of the form T equals A plus B times natural log of D that represents the data. Estimate how long it takes for the object to cool to 50 degrees Celsius. So this information to begin with is the data this information to begin with helps get to the data here. We're going to use this data, and then they say use this form of an equation. That's a natural log equation. So we're going to go to our calculator. We're going to go to stat edit, and let's enter in some of this data here. X is our D. I think, wait, hold on. Which one? T is in hours. Yeah, X is our D. So 160, 90. This is what makes it logarithmic rather than exponential. A constant increase on Y, whereas X has an exponential change, if you will. Okay, so with this one, now we're going to go to stat calc, and let's do that one, natural log regression. So our equation here in this form, A plus B ln X, A plus B ln D, whatever we're going to put, is T equals, my A is 12.59 plus, minus 2, this is a decent regression, minus 2.55 times the natural log of D, and D is our variable, right? So this is what I'm writing here. That's it for the equation. We could take a look at how this stuff looks on the graph. Let's put that equation into here. And let's zoom stat for that stuff. So this is where it goes. This is not exponential though. This is logarithmic, which means it goes below the x-axis. It doesn't have an infinite domain. It has an infinite range, that kind of stuff. It goes through them pretty well. So we are going to substitute here. They asked us to estimate how long it takes for the object to cool to 50 degrees Celsius. So now we're going to substitute 50 into here. 12.59 minus 2.55 times the natural log of 50. And we're going to figure out that time based off of this right here. So I have my calculator for that. We have the equation typed into y equals. I'm going to go to my table, substitute 50, and we get a time of 2.6, around 2.6 minutes, which is an interpolation and makes a little bit of sense, or hours, 2.6 hours, which makes sense for an interpolation for this data when you can see that 50 is between 56 and 38, and it's somewhere between 2 and 3 here. Number 34. Using tools. The f-stops on a camera, I'm glad we're just using the calculator stuff now, control the amount of light that enters the camera. All right, 2 hours. Let S be a measure of the amount of light that strikes the film, and let F be the f-stop. The table shows several f-stops on a 35 millimeter camera. Use a graphing calculator to find a logarithmic model, still natural log, of the form S, so still the same kind of stuff. S equals A plus B times the natural log of F. that represents the data. Estimate the amount of light that strikes the film when f equals 5.657. So nothing different from 33, guys. We're just going to go ahead and do the same stuff over and again. I'm not going to copy the data or the table. I'm just going to, because I don't have to do anything with it. I just got to type in the numbers. So for x, we have 1.414, 2.000, 2.828, 4.000, and 11.314. I've dabbled with camera work. I have a camera right here, obviously, but I don't do too many changes to f-stop, aperture, things like that. I have some automatic settings. I do more things for video, and I do a lot more things in post. But even then, I haven't touched this camera in a long time. I just pretty much record now. So, yeah, there's that. How are the Giants doing, by the way? I think 4-2 in the 8th inning. All right, let's finish before this game ends, and let's make sure it's not just an extra inning affair that keeps it that way. So we have the information. We can do a natural log regression equation here again, and I'm going to write this stuff. This is near perfect. Look at those numbers. It's as close to r squared being 1 as it can get. So I trust these numbers. Now that a value, here's the thing. It's still there. I can't call it 0, so I'm going to have to do some rounding. That's 0.000399, I'll put 4. 4 plus 2 I guess I'm using more numbers. 2.8852 times the natural log of f. So I'm putting these numbers here. I can't just put 0.00. Maybe I also can. How significant is that number? I guess not very. It's not very significant all told. You're only adding that amount to your answer in the end anyway. If we do some rounding to we'll probably round to 3 decimal places. Well, no, we're solving for s, right? When f is 5.657. So maybe that isn't significant. Maybe it's not a number that we should be substituting in there. And, and maybe we should. Anyway, so 0. But here's the thing. I'm going to use the calculator version. I just wanted to write out what the equation was regardless. I don't want to put 0. 2.8852 times the natural log of, and we're going to do 5.657. And by the way, these aperture f-stop things I'm familiar with. On my camera, 5.6 is one of the options. 5.6 is one of them. I forget all of them, but 2.8, I forget what I'm using right now. I might be using 2.8 right now on this thing when it gets blurry and stuff like that. I think I'm using 2.8 right now. I think 5.6 is one of the options as well. Anyway. Don't they also call that bokeh? I don't know. I'm kind of, you can correct me if you know anything about camera stuff. So we're going to go to the calculator. I'm going to use that equation here. And let's substitute 5.657. 5.657. 5.0001. So my S is supposed to be 5. 5 being the amount of measurement light strikes the film. Is that shutter speed? Are they talking about, light? Well, S is 5. I'm trying to figure out what that unit is. Amount of light. S equals 5. I like that it's S and 5. I know 5 light units. If you've ever seen, look up Brian Regan. I guess UPS works, but the punchline is girth. He's trying to ship something with UPS. He's a stand-up comedian, and he's trying to ship something through UPS. So he's calling them, having them pick it up, and they say like, we need to know the weight and the girth. And then in his stand-up thing, he's like, okay, I don't know how much it weighs, and nice long 4-second pause. I don't know what girth means, and most of us don't. It has to do with the distance around the object. I just like that. And so he later calls back and makes up numbers. He's like, 3 girth units. He's like, just pick this up. All right. The table shows the average weight in kilograms of an Atlantic cod that is X years old from the Gulf of Maine. Show that an exponential model fits the data. Then find an exponential model for the data. That sounds like we're not allowed to use the calculator for that. I could say, hey, this r squared is very close to 1 or something like that, but I feel like that's not what we're doing here. By what percent does the weight of an Atlantic cod increase each year this period of time? Explain. Okay, so show that it fits the data. you know, I'm going to show how much they're multiplying by from each one number to the other. 0.75, do this here, 1.079 divided by 0.751. If they said show that it does, then these must be pretty close to each other, close enough at least. We're multiplying here by about 1.44, and then here is 1.58. That's reasonable. This is 1.29, sort of reasonable. And then 3.438 divided by 2.198. 1.56. Reasonable. So exponential. Again, if we use the calculator and we find the r squared value or something like that, and it's greater than 0.95 or something, we'd say, yeah, that's really good. It's fine. It's fine. We're fine. We're good. Okay, come up with a model that fits the data. So for this part A, or the continuation of part A, I'm just going to choose the farthest end numbers. I don't know if that's kind of the way that we want to speak about that each time, but farthest end numbers are good for me. So y equals ab to the x power, and y equals ab to the x power. When you do substitution, we're going to say a equals 0.751 over b. Still 4 questions after this. So by substitution, we'll get 3.438 equals 0.751 over b times b to the 5th. So that'll leave with b to the 4th. B to the 4th equals, and I'm going to divide by 0.751 or whatever. 0.751. 3.438 divided by 0.751. And I'm getting 4.578. It's rounded. I'm taking the 4th root here. Everything I'm doing is in the calculator. It's in-house, man. So I'm raising this to the 1/4 power, 0.25 power, and that's 1.46. 1.46. Of course, it's rounded. A equals 0.751 over that number, 1.46. 0.751 divided by that answer. And I'm getting a value about 0.51. So my equation will be y equals 0.51 times 1.46 to the x power. Of course, there are some rounded values within, but that's my model. Part B, by what percent does the weight of an Atlantic cod increase each year in this period of time? Explain. The 1.46 is what's telling you it. So this thing here is also 0.51 times 1 plus 0.46 to the x power, which makes this thing 46% increase. And that's why we're adding it to 1 in that scenario, and that's how exponential functions work with regard to percentage increase decreases. That's not our first rodeo doing that. All right, 4 more questions. Number 36 on how do you see it? The graph shows a set of data points x and natural log of y. Do the data pairs x, y fit an exponential pattern? Explain your reasoning. They do. They do because the logarithmic y values are represented in a linear function, in a linear pattern with the x values. Okay, I wrote they do. They do what? They do the data pairs x, y fit an exponential pattern. Okay. Number 37. Making an argument. Your friend says it is possible to find a logarithmic model of the form d equals a plus b to the natural log of t for the data in exercise 33. Is your friend correct? Explain. We're going back quite a bit here. No. Did they swap d and t? They swap d and t. No. So your friend is incorrect. Your friend is incorrect. The original, the model in number 33 is logarithmic, and your friend is attempting to find the inverse, which would be exponential instead of logarithmic. So no. Sorry, friend. Your friend, my friend. My friend. My friend's been wrong quite a bit. Couple rights here and there, but wrong here. Number 38. Thought-provoking, aka open-ended. Is it possible to write y as an exponential function of x when p is positive? If so, write the function. If not, explain why not. Yes. Yes. Explain why. They have a common ratio of 2. So who cares? If p is negative, it'll still work. It's just a negative. You know, we haven't graphed negative exponential functions, have we? Oh, yeah, we have. We've done a couple. Common ratio of 2 times 2 times 2 times 2. R equals 2. Normally they say to write one, they say thought-provoking, come up with one. This just says, is it possible? Oh, if so, write the function. Oh, they did. I'm sorry. Okay. So anyway, so I guess we don't have to explain that. So if it has a common ratio of 2, that means your the b value is 2, right? And I don't think it says write the function. So this is based off p. Your a value is p over 2. And I say that because when x is 0, you got to divide by 2 to get there. So that's p over 2, 1/2 p. So as far as the equation, it's y equals p over 2 times 2 to the x power, like that. Or 0.5 p or whatever you want to put, 1/2 p, something like that. But that would be the result of that one. Okay, now I understand it. I was not listening. Now, you could also do other things with this, right? If we're dividing by 2 one more time like this, look, you can do this. You could also rewrite it as p times 2 to the x over 2. And I'm saying it like that because that's also 2 to the first power. When these two divide, the exponents subtract. So I could write this also as y equals y equals p times 2 to the x minus 1 power. P times 2 to the x minus 1 power. It's up to you how you want to do your shifts. These are both the same thing. One is shifted 1 unit to the right, but you're starting at a higher number with p. The other one here is like that. And you can do it based off this x minus 1, like that right there. So it just depends on how you choose to go about it. All right, the last question, number 39, in critical thinking. Ooh. Only 2 parts, though. You plant a sunflower seedling in your garden. The height h in centimeters of the seedling after t weeks can be modeled by the logistic function this. Okay, you guys don't know what logistic functions are. I'm just going to call it out right now. A logistic function is a function that has 2 asymptotes like this. A lot of real-world models come up in this format. Let's say it's at 0. Come up in this format where there's like an increase this way, and then at this side it decreases again, and it takes this kind of form on. It has 2 asymptotes to them. I'm not very good at graphing them. Hopefully you get to use a graphing calculator. But logistic functions of this is pretty natural for something. It might take off slowly, and then eventually there's only so much of it that can take off, so it flattens out. Things don't go forever. Anyway, logistic function. So h of t equals 256 over 1 plus 13e to the negative 0.65 t. Find the time it takes the sunflower seedling to reach a height of 200 centimeters. Okay. So we're solving for t. We're supposed to substitute 200 for h. This kind of goes back to the last. This fits a little bit more. The first question fits a little bit more in the last section to me, I think. Whichever one we were solving for. I'm going to multiply both sides by this 1 plus what have you. And then I can divide both sides by 200 at the same time. So I'll say 1 plus 13e to the negative 0.65 t equals 256 over 200. Of course, that can reduce. We'll have to work out what that reduces to. I'm thinking divide by 4 at even more. We'll figure it out in a second. I'm going to subtract 1. Actually, as I subtract 1, let's see. 256 over 200. Okay, that's 1.28. So 1.28 minus 1. And we'll divide that by 13. So e to the negative 0.65t equals 0.28 over 13. I'm sure that doesn't reduce very well. I can natural log both sides. And this will give me negative 0.65t equals natural log of that. If you would like to write them separately, it's natural log of... I'll keep them together. I don't want to get clever here. And then we'll divide both sides by negative 0.65. So t is natural log of 0.28 over 13, all divided by negative 0.65, which is about something. So let's see what this number is. I got natural log 0.28 divided by 13, close the parentheses, and divide it all by negative 0.65. I'm getting about 5.9 weeks. It's going to take about 5.9 weeks for the seedling to do something, something, something. What is it? Plant a sunflower seedling, the height. The height will reach about 200 centimeters after 5.9 weeks. All right, use a graphing calculator to graph the function. Interpret the meaning of the asymptote in the context of the situation. So, as I stated, logistic functions have technically two asymptotes on them. So, let's go ahead and do that. So, 256 over 1 plus 13 times e to the negative 0.65x. I don't know a graphing window here. I'm going to guess that 256 is a part of the y value stuff. I'm kind of forgetful on how logistic functions are presented. So I'm going to have to just look at this a little bit. We obviously go at least to 200 for x. So let's check out 400 and see what's going on. Whoa. Okay, there's the logistic function doing logistic things. Let's turn off the stat plot. X is the weeks, not the height. So let's do that again for x. Let's go to like 10. All right, there's some appearance logistic. Let's zoom out just a little bit here. I'm going to go some negatives. I'm going to go from negative 2 to positive 12 here about. And the 0.256 is still pretty good. You'll see a little bit more of that here. You see the curve up and curve down like that and across. That's what this thing does. So it has two asymptotes. It has two asymptotes here. And the asymptotes represent the height that it starts off as a seedling. And I guess it starts at time 0 right there. And then what it can only reach to. Same with us as people, right? We might hit a growth spurt and then we slow ourselves up each time with our height. I've hit my maximum height, I guess, unless I increase by millimeters at a time. But that's the appearance of that graph. When it says use it to graph the function, I'm going to copy and paste this. And only the part of the window range that I actually care about. Actually, let's increase the window more because I know 256 was that top and it still is the top. But let's increase x to about 15. And I don't think negatives actually do matter for what we're talking about. So let's go from that to that. And again, you can see it flattening out at 256 there. So that's a good idea of the graph. Let's copy and paste that over here. Hopefully I was still on the graph screen. Otherwise you saw nothing that I was changing windows on. So that represents, or the asymptote of 256. The asymptote of y equals 256, the maximum height of the sunflower. Now, can it actually hit that height? I guess not technically, but that's the one that it's reaching closer and closer to over time. That'll be it. All right, guys, that'll do it for this one. This is the end of the section and therefore the end of the chapter. A lot of tougher parts to hit there when it came with the modeling the data without using the calculator itself. Apologies on the slowdowns there. It started off well and kind of tapered. So do with this information as you will. It's my first time going through it as well. I'm just as aggravated on some of those ones as you are. But guys, I'm all done. That'll do it for this one. Take care. Thank you so much. I'll see you in the next one.